Hello, it's Medicosis Perfectionalis, where medicine makes perfect sense. Welcome back to the third video in my organic chemistry for MCAT playlist. This playlist is for anyone studying organic chemistry, but it is particularly made with the students of MCAT and DAT in mind. In the previous video, we talked about the systematic IUPAC naming system of organic molecules. Today, it's time to talk about isomerism. What does iso mean? Similar. What does mer mean? It's a piece, as in centromere. And what does ism mean? A condition. So isomerism is a condition of similar particles, similar pieces. So without further ado, let's get started. If you wish to converse with me, define your terms. So let me define my terms. Isomerism, a condition of similar pieces. What do you mean? I mean, we'll talk about organic molecules or compounds that have the same chemical formula but different structure. For example, here the NH2 group is on the left, but it's here on the right. That's the different chemical structure, but they have the same chemical formula. How many carbons do we have here? Here's 1 and 2 in either one. How many hydrogens? 1, 2, 3, 4. 1, 2, 3, 4. So it's the same. How many oxygens? 1, 2, 1, 2. How many nitrogens? Just one, just one. You see, they have the same chemical formula but different structure. Next, what does the word chiral mean? The word chiral means just like your hand. It literally came from a Greek word that means hand. Look at both of your hands. Are they mirror images of one another? Yes, they are. Are they superimposable? No. If I try to superimpose one on top of the other, I'll find that the thumb here is on the left, but here it's on the right. So no, they are not superimposable, i.e. the left hand is not gonna fit into the right hand glove because they are not superimposable. Third, no internal plane of symmetry. If I imagine a line dividing a singular hand into two halves, the right half is not the same as the left half. For example, this one has a thumb, but this one has a pinky finger. They are not the same. They are not symmetrical. So mirror images is talking about the left hand compared to the right hand, but internal plane of symmetry is talking about a singular hand. Next, what does a chiral mean? A chiral mean the opposite. Superimposable. What if I do have an internal plane of symmetry, like in a spoon or a fork? I can imagine a line dividing the spoon into two equal halves, and the same thing applies for the fork. I can imagine a line dividing the fork into two equal halves. If we have an internal plane of symmetry, therefore it is a chiral. Next, mirror images. That's easy. This is a reflection of this. Look at OH here, it's closer to the mirror. And on this side, it's closer to the mirror. How about the CH3? Far away from the mirror and far away from the mirror. Why are they reflected? Because here we have the methyl group on the left, but the methyl group is here on the right. The inverse is true for OH. The hydroxyl group is on the right here, but is on the left here. These are mirror images. Superimposable mean they look identical when placed on top of one another, but your hands are not superimposable on one another. Next, stereoisomers. What does the word stereo mean? It means solid, and isomer mean similar pieces. What do you mean by stereoisomers? I mean, they have the same atoms linked together in the same way, but organized differently in space. For example, one could be the non-superimposable image of the other. Enantiomers are subtypes of stereoisomers. Enantiomers are non-superimposable mirror images. Please memorize this sentence. Enantiomers, non-superimposable mirror images. Optical activity is the ability of the molecule to rotate the plane polarized light either clockwise or counterclockwise. Dextro or Levo. D or L. D means dextro, L means Levo. Positive or negative. Rotate to the right, rotate to the left. In order for you to have optical activity, you need to have a chiral center or centers and no internal plane of symmetry. But what if I have no chiral centers? Then you have no optical activity. What if I have an internal plane of symmetry? Therefore, you are not optically active. Don't forget the word isomer means similar to, and in order to be similar to, we have to talk about two compounds or more. But simply one compound cannot be called an isomer. Well, isomer compared to what? So think of the word isomer as equivalent to richer. I cannot be richer by myself. I have to be richer compared to someone else, or poorer compared to someone else, or as rich as someone else. So isomers are always comparing one molecule to another. One molecule cannot be an isomer by itself, but two molecules could be isomers or could be non-isomers. Can I have three molecules that happen to be isomers? Absolutely. If you remember my video on stereochemistry, in my biochemistry playlist, we have talked about D versus L. For example, most of your carbohydrates in the body are in the D form, but the amino acids in your body are mostly in the L form. And we also talked about R versus S, and we shall discuss this in detail in the next video. Remember, D versus L can only be established experimentally in the lab by a polarimeter, which measures the angle of rotation of the plane polarized light. Rotate me to the right, D, Dextro, or rotate me to the left, L, Levo. How about R and S? Can we determine this in the lab? No, this is determined with pen and paper, based upon the priority of the groups around the chiral carbon. More on that in the next video. If I rotate the plane polarized light to the right, I am Dextro, to the left, I am Levo. Just because I am D, Dextro, doesn't necessarily mean that I am R. Let's start by answering the questions of the previous video. Can you name this organic compound? The IUPAC name, please. Step number 1, give me the longest chain of carbons. Here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even if you try numbering them from here to here, you'll also find 10 carbons. 10 means dec. Next, I need the suffix and the prefix. Should I number from right to left or from left to right? It's a matter of priorities, and if you remember, hydroxyl group wins. So I should start numbering from here because it will give me the lowest possible numbers, which is 2, 5, and 9. The highest priority functional group is the OH, the alcohol group, so it will give me the suffix. Since this alcohol group is attached to carbon number 2, this is 2-ol. How about the double bond? It's attached between 9 and 10. What's the lowest possible number? 9. So this is dec9-ene from alkene to ol. Okay, how about this group right here? It's an ethyl group because it has 2 carbons. It's attached to carbon number 5 and therefore 5-ethyl. Dec9-ene to ol. God bless it. Another question from the previous video. Pent-2-ene has how many methyl groups and how many methylene groups? Please pause. First, let's draw the molecule. It's pent, so it has 5 carbons. Here's 1, 2, 3, 4, and 5. Between 2 and 3, we have a double bond. So let's number from here, 1, 2, 3, 4, and 5. Between 2 and 3, I have a double bond. Amazing. And the rest is history, just put the H's. This is CH3. This carbon is already making 3 bonds, so it needs another H. This is making 3 bonds, it needs another H. This is only making 2 bonds, it needs CH2. And this is only making 1 bond, so it needs CH3. And this is my pent-2-ene. Now the questions are, how many methyl groups? What is methyl? Methyl is CH3. So I have 1 methyl group, 2 methyl groups. So the first part of the question is 2 methyl groups. How about methylene groups? What is methylene? Methylene is CH2. How many CH2s do I have? I only have 1 CH2, so here I put a 1. So the correct answer here is choice F, as in F me. The last question from the previous video is, here is a graph. The number of carbon atoms in the hydrocarbon is on the x-axis, but the number of hydrogen atoms in the hydrocarbon are on the y-axis. And you have 2 graphs, graph X and graph Y. They represent 2 homologous, i.e. only carbons and hydrogens, nothing else. No oxygen, no nitrogen, nothing else. And then these are representing what? It is alkane, alkene, alkene, alkane, etc., respectively. Please pause and try to answer this yourself. Let me start by graph X. When I had 2 carbons, I had 4 hydrogens. When I had 4 carbons, I had 8 hydrogens. When I had 6 carbons, I had 12 hydrogens. So it follows this formula, CnH2n. And this is the formula for alkenes. So the first part has to be alkene. That's for graph X. How about graph Y? Well, the same thing. Let's start with 2 carbons. When I had 2 carbons, I had 2 hydrogens. When I had 3 carbons, I had 4 hydrogens. When I had 4 carbons, I had 6 hydrogens. When I had 5 carbons, I had 8 hydrogens. And when I had 6 carbons, it was 10 hydrogens. So it's following the formula CnH2n minus 2, which is the formula for alkyne, which makes the correct answer E as in echo. Before watching this video, please refer to my stereochemistry video in my biochemistry playlist. This playlist has everything in basic biochemistry, from titration of amino acids all the way to the Krebs cycle and the electron transport chain. Do you remember these? D-glucose, D-galactose, D-mannose, and D-fructose. All of these are isomers. Why? They have the same chemical formula. All of them have 6 carbons, all of them have 12 hydrogens, and all of them have 6 oxygen. However, the structure is different, as you see. So therefore, these are stereoisomers. Stereo means solid. What do you mean by solid? I mean they are the same atoms linked in the same way, but organized differently in space. For example, left, right versus right, left. Remember this? This is called the fissure projection. And in the fissure projection, the horizontal lines are wedges coming out of the page at you. But the vertical lines are dashes, which means they're going into the page. Mnemonic, the van, vertical, dashed vertically into the lake. So the vertical lines are dashes. Therefore, the horizontal are wedges. Look at these. Which ones are the horizontal ones? The H and the bromine, which means hydrogen and bromines are coming out of the page, just like this. But who's going into the page? The chlorine and the methyl, just like that. From my chemistry playlist, I hope you remember the difference between physical properties and chemical properties. Physical properties can be measured, observed, or changed without altering the identity, i.e. the chemical composition of the substance. So the chemical composition will remain the same. Rotating the plane polarized light to the right or to the left, i.e. optical activity, is a physical property. But chemical properties are different. When I change a chemical property, it gives the molecule a new identity, i.e. a new chemical composition, such as reactivity, toxicity, and flammability. So what are isomers? They have the same chemical formula, but different structure. Stereoisomers are subtypes of isomers, as you can see in this Venn diagram. Same atoms linked in the same way, but organized differently in space. All of these are isomers. Isomers could be constitutional isomers or stereoisomers. Stereoisomers could be enantiomers or diasteriomers. Diasteriomers could be epimers, which are a special case of diasteriomers, as we have discussed before in my video on stereochemistry. So isomers are stereo or structural, i.e. constitutional isomers. Then the stereo are enantiomers or diasteriomers. The diasteriomers could be epimers or otherwise. What is the definition of enantiomers that we have just memorized? Non-superimposable mirror images. What are diasteriomers? They are not mirror images, they are not identical, and they are not superimposable. They differ in at least one chiral carbon, but they do not differ in all of the chiral carbons. So they have to differ in at least one. But what if they differ in exactly one chiral center? Then they are epimers. Epimers differ in exactly one chiral carbon. And epimers are a subtype of diasteriomers, because one is also part of the definition of diasteriomers. So isomers are stereo or constitutional, i.e. structural isomers. The stereoisomers could be enantiomers or diasteriomers. The diasteriomers, if they differ in exactly one chiral center, they are called epimers. But diasteriomers also involve geometric isomers, the Z versus E, trans versus cis. Look at this double bond. I have the groups coming out on the same side. Both of them are above the double bond. On the same side is Z. But look at this. Here's the double bond. There's one group sticking up, another group sticking down. Oh, they are across, opposite to one another. E cross E. And the old system is trans when they are opposite or cis when they are the same. The old system, cis versus trans, is okay if you have one substituent. But if you have more than one substituent, then E versus Z is better. And this is the most important slide in the entire stinking video. If you can make sense of this nonsense, you'll be in a pretty good shape. All of the following are isomers, meaning what? Same chemical molecular formula, but different structure. If the isomers have the same atomic connectivity, i.e. the same backbone, they are stereoisomers. But if they have different atomic connectivity, different backbone, then we're talking constitutional isomer or structural isomer. These are synonyms. For example, look at this butane 1-ol versus butane 2-ol. The atomic connectivity is different because here the hydroxyl group is connected to carbon number 1, but here it's connected to number 2. So different atomic connectivity, which makes them constitutional or structural isomers. By the way, the least similar of all the isomers. Next, let's dig deeper into stereoisomers. Stereo means solid. What do you mean by solid? I mean they are the same atoms, linked in the same way, but organized differently in space. And then we gotta ask ourselves the next question. Do I need to break bonds in order to interconvert between one isomer and the next? If the answer is yes, it's a configurational isomer. If the answer is no, it's a conformational isomer, which means there is no need to break bonds. Conformational isomers, by the way, are the most similar of all the isomers versus constitutional isomers, which are the least similar. Why do we call the conformational isomers or conformers the most similar? Because basically it's usually the same molecule at different points during its natural rotation, as we'll discuss soon when we talk about the Newman projections. Same molecule. Okay, let's rotate a little. Let's rotate more. Let's rotate even more. Oh, it's the same molecule at different points in natural rotation. So all of these are conformers. They conform to the same molecule at different points during its natural rotation. And here we are rotating around a single bond. And recall that single bonds are freely mobile. You can rotate around a single bond all day long. Keep this in mind because soon we'll talk about E versus Z across a double bond. And a double bond is immovable bond. But singular bonds or sigma bonds are freely mobile and freely movable. Let's say that I do require bond breakage in order to interconvert, therefore I'm configurational isomer. Then, if I am, have you memorized the definition? Non-superimposable mirror images. These are enantiomers. But what if they are not mirror images and they differ in one or more chiral carbons? These are diastereomers. If they differ in exactly one chiral carbon, we call them epimers, which is a special case of a diastereomer. Then we have an immovable bond, such as a double bond, as you see here, or a ring structure, as you see in cycloalkanes. Then we'll have Z versus E, or cis versus trans, and these are called geometrical isomers. Look at these epimers. What's an epimer? Oh, they are diastereomers that differ in exactly one chiral carbon. Look at this. They are similar when it comes to bromine. However, look at this chiral carbon. Oh, this is just one chiral carbon at which they are different. One is a wedge, the other is a dash. So therefore, these two are epimers, which are a special type of diastereomers. How about mesocompounds? A mesocompound is a compound that has an internal plane of symmetry, just like that. Here's the internal plane of symmetry. The left half is identical to the right half. Think of a spoon or a fork. Question, what kind of isomers are these? Please pause. And the answer is, these are constitutional or structural isomers. I have 4 carbon atoms here and 4 carbon atoms there. But here the 4 carbons form a straight chain, but here they do not. Yes, it's a straight chain here, but we have a branch at number 2. Here we do not have a carbon branch at number 2. Recall that constitutional isomers are the least similar of all the isomers. If you write down the chemical formula for both, they are the same. And here are the constitutional isomers. The only thing that they share is their molecular chemical formula. How about these? What type of isomers are these two compounds? The answer is, it's the same thing, constitutional or structural isomers. They share the exact same chemical molecular formula, but they have different structure. They have the same number of carbon atoms, the same number of hydrogen atoms, and the same number of oxygen atoms. How about these doozies? These are also constitutional or structural isomers. All of them share the same chemical molecular formulas. Here's 1, 2, 3, 4, 5, and 6. So it's an alkane, C6H, 2N12 plus 2, 14. And there you go. What about these two doofuses? What kind of isomers are they? Please pause. If you have watched my biochemistry playlist, you will recall that this is a D-glyceraldehyde and this is an L-glyceraldehyde. Dextro versus Levo. Rotate me clockwise, rotate me counterclockwise. Rotate whom? The plane polarized light. And you can measure this optical activity via a polarimeter. If the angle of rotation here is positive 60, for example, then it has to be negative 60 here. And therefore, these two are configurational isomers. This is HOH, but this is OHH. Are these two mirror images? The answer is yes. Are they superimposable? Well, the H cannot fit over the OH, neither can the OH fit over the H. So no, they are non-superimposable. Look at that. Here are the same two doofus molecules, D-glyceraldehyde versus L-glyceraldehyde. Non-superimposable mirror images is the definition of enantiomers. All the previous questions, by the way, are in the previous video in this organic chemistry playlist. Here is another one. A hydrocarbon chain has two chiral carbons. Therefore, this compound has how many possible stereoisomers with a common backbone? How do we answer this? Well, if you remember, there was a rule. It's called 2 raised to the n power. What is n? It's the number of chiral carbons. And they told me here that the number of chiral carbons are 2 chiral centers. So it is 2 to the power of 2, which gives me the answer of 4. So I have 4 possible stereoisomers. But what if 2 of these are mesocompounds? So imagine that this is 1, 2, 3, and 4. All of these are stereoisomers. But 2 and 3 are identical, i.e. mesocompound, because they have an internal plane of symmetry. Therefore, how many possibilities? Here's 1, here is 2, because they are considered the same identical thing, and here is 3. So the answer should be 3 if you know that there are mesocompounds. But here they told me nothing of this sort, which makes 4 still the correct answer. How about these lovely people? What type of isomers are these? Okay, please pause. What do we call the same compound at different stages of rotation? We call them conformers, i.e. conformational isomers. Just like that, the Newman projections of the same exact thing rotating freely around single bonds is conformational isomer. And conformational isomers or conformers are the most similar types of isomers. How about these? What types of isomers are these? And the answer here is, they're also conformers. It's the same molecule, just assuming different shapes. For example, this is the chair conformation. This is the boat, and this is the twist boat. All of these are cyclohexane. Same molecule, just at different angles of rotation, which makes the 3 conformers. There you go. They are conformational isomers. Question: which of the following is the most energetically stable and therefore favored, energetically speaking? And the answer is choice A is the most stable and therefore favored. It exists at low energy, i.e. low maintenance. That's why we like it. Think of it this way. If you sit on a chair, you are the most stable. But the boat, oh no, the boat floating on water is very unstable. It is vulnerable to the winds and the whims of the sea. Boat is not stable, but the chair is. Next, let's talk about the Newman projection. Look at that. Here is a single bond. That's important. It's not double bond. This is a single bond, which means freely mobile. I can rotate around it easily with no problem whatsoever. It is not stiff. It is mobile and flexible and movable. And let's say that I will look at this molecule this way. So here's my eye. Which one is the front carbon? C2. And which one is the back carbon? C3. So let's draw the front carbon first in red color. So the carbon in the center, here it is. I have CH3 up. Let me put CH3 up here. And therefore, which ones should I put down? Well, H and H. The thing that is sticking out of the page should go to the right side, and the thing that is sticking into the page should go to the left side. And this is the front carbon with all of its substituents. Now let me draw the back carbon in a different color, the blue color. Okay, I have something sticking down, and that's a methyl group. Let me draw methyl right here. And therefore I'll have 2 things sticking up, and both are H's. Here's an H, and here's another H. And this is called the Newman projection, made possible by the fact that single bonds are freely mobile. I can rotate around a single bond easily, which means all of these projections are of the same molecule, this doofus right here, at different times during their rotation, which makes them conformers. Think of methyl groups as two bulky things that hate one another. When one is overlapping the other, this is similar to a morbidly obese person sitting in front of you in a movie theater. Will you be able to see anything? No, I hate myself, which means not favored because it's high energy and therefore high maintenance. But what if one methyl group is sticking up and the other methyl group is sticking down? Oh, this is the best position ever, i.e. less energy, i.e. low maintenance, i.e. the most stable. And we like it very much. One is up, one is down. This is called the staggered conformation. And since one is up and one is down, we call them anti-periplanar from one another, and this is called the anti-staggered conformation. What's the angle between this methyl and this methyl? 180 degrees. But what if that methyl came here, so that the distance or the angle between two methyl groups is only 60 degrees? This is called gauche. So are these two hugging one another like this? No, they are not hugging one another yet, therefore staggered. But are they anti-periplanar, i.e. one is down, one is up with an angle of 180 degrees? No, they are not anti-periplanar, they are gauche. So this is the gauche staggered conformation. Now look at the methyl group. Now both of them are in front of one another. Two bulky groups hugging one another. I will not be able to see in front of me because there is a morbidly obese person in front. So this is totally eclipsed. He has totally eclipsed me. Think of the solar or the lunar eclipse. One object is in front of the other. It's in my path. But what if the angle is 120? Then it's eclipsed but not totally eclipsed. But why is this eclipsed and this is staggered? Because here we have no overlap. Here is just one thing at this level. But look at that. At this level, I have two groups. At this level, I have two groups eclipsing one another. But here, no one is eclipsing anything. It's staggered. Staggered is more favored than eclipsed. Anti-staggered is the most favored. Totally eclipsed is the least favored. So let's draw this. Here is the rotation on the x-axis and the potential energy on the y-axis. If something is way up here, we call this high energy, which means high maintenance, which means not favored. But if something is down here, it means low energy, low maintenance, and therefore more favored. If you want to learn more about the concept of entropy and what is high entropy versus low entropy, please refer to my chemistry playlist. Which conformer has the lowest energy possible and therefore the most favored? The one that has anti-periplanar methyl group. One is up, one is down, with an angle of 180 degrees between them. So this is called the staggered, and since they are anti-periplanar, we call this the anti-staggered. Least energy, we're down here, and therefore the most favored. Let me rotate this methyl group a little and put it here. Oh, so this makes the distance between them 120. This is eclipsed, but not totally eclipsed yet. And because it's eclipsed, the methyl group came closer to one another, so they hate one another, which makes them high energy, low maintenance, less favored. Let me rotate this methyl group again and put it here. Oh, so it looks like this. Is anything eclipsing anything? No, we have free space between them, so it is staggered. What's the angle? 60 degrees. Staggered is lower energy than eclipsed. Because we're free here, relatively speaking, no one is eclipsing anyone else. Then let me rotate this methyl group again. Oh, this is the worst. This is someone sitting exactly in front of me and I cannot see. This methyl group is eclipsing and hiding this methyl group, so that's not good. This is totally eclipsed, which means high energy, which means least favored. Let me rotate this methyl group another 60 degrees. Oh, it's gauche again. Okay. Am I eclipsing you? No, therefore staggered. Staggered is better than eclipsed, i.e. staggered is more favored and lower energy than eclipsed. Let me rotate CH3, another 60 degrees. Oh, look at that. This is eclipse, but it's not totally eclipsed because the methyl group is not hiding the other methyl group. Then let me rotate it another 60 degrees. Look at that. I'm back to the anti-periplanar, the anti-staggered, which is the lowest energy and therefore the most favored. So which one of these is the highest energy and therefore least favored? Totally eclipsed. Which one is the lowest energy and therefore most favored? It is the anti-staggered. And which two are in between? The eclipsed versus the gauche. Which one is more stable? The non-eclipsed, i.e. the gauche. If the difference in potential energy between one conformer and the other is very small, then it's easy to overcome this energy difference, which means this is more likely to become spontaneous at room temperature. But at absolute 0 degrees Kelvin, it'll be extremely difficult to overcome the energy difference, which means no rotation will happen in reality. Next, let's talk about cyclic conformations. Remember that there are many types of strains in organic chemistry. Let's just talk about the ring strain. The ring strain could be caused by angle strain, torsional strain, or a non-bonded strain, aka steric strain. What causes the angle strain? It's when the bond angles deviate from the ideal. How about torsional strain? Oh, rotation, do you remember? Eclipsed versus gauche. When the two methyl group are in total eclipsed, the torsional strain is at maximum, which means least favored. And then we have the non-bonded strain or the steric strain caused by the famous van der Waals forces, which are repulsion forces. Why? Because we have non-adjacent atoms that compete with one another for the same space. Let's talk about some examples of the non-bonded strain. Look at this. This is a boat conformation. Between the upper pole and the upper pole, here's a flag at the pole and here's a flag at the opposite pole. They interact with one another. Repulsion, i.e. van der Waals, i.e. steric strain exists between the two, i.e. non-bonded strain, which makes this less energetically favored. The boat is unstable, but the chair is stable. Because look at this. Here's a flagpole here, but we have hidden the other one down there. Oh, less strain between them. That's why the chair is the most stable. And if you remember my biochemistry videos, especially on carbohydrates, we have talked about equatorial versus axial. And I've told you that the equatorial is more stable and more favored than the axial. Therefore, chair is better than boat and equatorial is better than axial. Let's lump these two together. There is nothing more stable or more favored than sitting on a chair at the equator. Chair and the equator, the most stable. But floating in a boat in the sea is very unstable. Why unstable? Because of flagpole interactions, which are steric strains. And this slide is from my biochemistry playlist. This was alpha-D-glucose. Why is this alpha? Because it's axial and down. But this was beta. Why was this beta? Because it was equatorial and up. Axial means vertical in this conformation, and equatorial means more horizontal. Which one is more stable? Remember, there is nothing more stable than having a chair. That's a chair on the equator. The equatorial is more stable. The beta was beautiful. But the alpha was ASS, which means donkey. And remember that going from one chair to another chair was called muta-rotation or chair flip. Here's another question. Which of the following is more energetically favored? Is it this chair or this chair? Please pause. This one is axial. This one is equatorial, which makes B more stable because it's equatorial. And why is the equatorial more favored? Because we have less flagpole interactions. What does that mean? It means that if you look at A, look at this bulky group, it is bulging axially. And this one is also axial. Axial and axial equals flagpole interactions, which means not very stable. But look at B. This is bulging axial, but this is bulging equatorial. Less flagpole interactions, which means more stable. How about this one? Which of these two compounds is more energetically favored? Look at the bulky group. Here the bulky group is equatorial, but here it is axial. Which one wins? The equatorial is more stable due to less flagpole interactions. So I can say it in many ways. I can say that the equatorial is more stable, i.e. low maintenance, i.e. low energy, which means more stable and more favored. So all of the Newman projections and boats and chairs are conformational isomers. Now let's turn our attention to configurational isomers. What does the word chiral mean again? It means just like your hands. They are mirror images of one another, not superimposable on one another. The left hand cannot fit into the right hand's glove, and there is no internal plane of symmetry. But what if I am like a fork with an internal plane of symmetry in the middle? Then you are achiral or non-chiral. What is the chiral center or the chiral carbon? It's a carbon that is an asymmetric core of optical activity. There is no internal plane of symmetry. You cannot imagine any line that will divide this molecule into two identical halves. If I draw the line like this, on the left I have hydrogen and methyl, and on the right I have iodine. They are not symmetrical. There is no internal plane of symmetry here, no matter how hard you slice it or dice it. Look at this image and its mirror image. These two are configurational isomers. Do you remember that? That's a chiral carbon. That's a chiral carbon. These two are mirror images. Again, most carbohydrates in your body are D, but most amino acids in your body are L. Next are enantiomers. Enantiomers are subtypes of configurational isomers. What's the definition of enantiomers? Non-superimposable mirror images of one another, just like D-glyceraldehyde versus L-glyceraldehyde. HOH versus OHH. Where's the chiral center? Here is my chiral carbon. Does this molecule have an internal plane of symmetry? No, I cannot imagine any line that will divide this into two equal halves. It's not going to happen. And that's why this molecule as a whole is chiral, and this molecule as a whole is chiral. In the next video, we'll talk more about the difference between absolute configuration and relative configuration. If I put these two molecules under a polarimeter and see how they rotate plane polarized light, I will find that one of them rotated to the right and one of them rotated to the left. One of them is positive, the other is negative. One of them is Dextro or D, the other is Levo or L. How many chiral carbons exist here? Only one chiral carbon, so let's put one here in place of the N. 2 to the power of 1 equals 2, which means I only have 2 possible enantiomers here, or 2 possible stereoisomers. But what if I had 2 chiral centers? Then I'll have 4 possible stereoisomers. How about 3 chiral centers? 2 raised to the third power is 8 possible stereoisomers. Enantiomers, they may rotate the plane polarized light to the right, dextro, or clockwise, or right, or dextrorotatory, or positive, or simply D. Or they can rotate the plane polarized light counterclockwise, or left, or levorotatory, or negative, or L. So the angle could be positive, or the angle could be negative. Okay, positive what? Is it positive 30, positive 40, positive 60, or how much? To know how much, you need to calculate the specific rotation angle. And this is directly proportional to the alpha, which is the angle observed using the polarimeter in degrees. But this specific angle of rotation is inversely proportional to the concentration of the D-glyceraldehyde or whatever compound you're working with, measured in grams per ml. Remember that concentration always equals amount over volume. And this specific rotation angle is also inversely related to the length of the path, i.e. the length of the tube through which the plane polarized light has to pass. And this length or distance is measured in decimeter. Remember that deci means 1/10 of. In this case, it's 1/10 of a meter. You need to write this equation many times because they ask you about it on the exam. If I increase the observed angle, what's going to happen to the specific rotation angle? It's going to go up. But if I lower the length of the tube, what's going to happen to the specific rotation angle? It will go up. There is a medication we use in medicine called racemic epinephrine. What does the word mean? It means this is a mixture of half D-epinephrine and half L-epinephrine. Oh, so it's 50-50. 50% dextro and 50% levo. 50% of the molecules in the drug will rotate the plane polarized light to the right. The other half will rotate to the left. Therefore, overall, they cancel one another and the entire racemic mixture has no optical activity whatsoever. For example, positive 50 will cancel the negative 50 and will end up with nothing. Look at the enantiomers. Suppose that one enantiomer rotates the plane polarized light to the right, the other to the left. And we'll combine each of these enantiomers with an enantiomer with positive optical activity. Positive and positive will give me 2 positives. Negative and positive will give me negative positive. Look at this. Each one has 1 positive. However, This one has a positive here, but this one has a negative here. Oh, so they differ in at least one, but not all chiral carbons, and therefore we have made diastereomers from enantiomers. And now we're talking about diastereomers. They differ in at least one, but not all chiral carbons. Diastereomers have more than one chiral center. Do they differ in all of them? No, they differ in more than one, or one, but not all of the chiral carbons. And since they differ, therefore they'll have different physical properties. And if they have different physical properties, it means we can easily separate them physically via filtration, crystallization, or distillation. And because they differ, therefore they have different chemical properties. But by the way, don't forget, these are still isomers, and that's why they may behave similarly in some reactions, because chemical properties depend on what? On the functional groups. They have the same functional groups. That's why in some chemical reactions they can behave very similarly, even though they differ. So the moral of the story is diastereomers always have different physical properties, but enantiomers always have similar physical properties, with only one exception: rotation of plane polarized light. Look at these four molecules. L-erythrose versus D-erythrose. One is a mirror image of the other. Are they superimposable? No. Look at this H. It will not superimpose on the OH. So these are non-superimposable mirror images, which means they are enantiomers. Are they mesocompounds? Well, let's see. Can I put an internal plane of symmetry here? No. Can I put an internal plane of symmetry here to divide them into two equal halves? No. If I do this, one half will have CHO, the other will have CH2OH. So no, there is no internal plane of symmetry. So therefore these two are enantiomers and they are not mesocompounds. Let's look at these two. Same story. They are non-superimposable mirror images, therefore enantiomers. Are they mesocompounds? I cannot imagine any internal plane of symmetry. Therefore, no, they are not mesocompounds. They are enantiomers, which means they can rotate the plane polarized light and they do have optical activity. But look at these two. Are these two mirror images of one another? Well, think about this. It's HOH, so here's HOH. That's not a mirror at all. They are not mirror images. Are they superimposable? Well, the OH can superimpose on OH, but the OH cannot superimpose on H, so no, they are not superimposable, making these two diastereomers. So these two together are enantiomers, these two together are enantiomers, and these two together are diastereomers. Now let's look at L-erythrose and D-threose. OHH, OHH. OHH, HOH. If they differ in precisely one chiral center, they are epimers. And epimers are a special case of diastereomers. So, 2 and 3 are diastereomers. 1 and 4 are also diastereomers. They are a special type of diastereomers known as epimers. Between 1 and 2, enantiomers. 3 and 4, also enantiomers. Got it? Let's compare between enantiomers and diastereomers. What's the definition of enantiomers for the gazillionth time? Non-superimposable mirror images, but diastereomers are not mirror images. Diastereomers are different. They have different physical properties, and which means we can separate them via filtration, crystallization, or distillation. And they have different chemical properties, although they might behave similarly in some reactions because they carry the same functional groups. Enantiomers are non-superimposable mirror images. They have the same physical properties except optical activity. They have the same chemical properties except reactions in chiral environments. So optic activity makes a difference. Yes, you can rotate the light to the right or to the left. If one of these enantiomers rotated the light to the right, then the other one has to rotate it to the left. If one is positive 50, the other has to be negative 50. But this is not the case with diastereomers. If you know that one of them rotate positive 50, you cannot predict the other one. It could be negative 50 or it could be something else. There is no way of predicting it. You have to measure it experimentally using a polarimeter. Another question, what kind of isomers are these? Oh, look at these. On the same side. Z alkene. How about this? One is up, one is down. E cross from one another. So this is E. Z versus E is an example of geometrical isomers, as you see here. Z versus E, or cis versus trans. These are geometrical isomers. It has to be an immovable bond, such as a double bond or a ring structure, versus single bonds, which are freely mobile And that was the idea behind the Newman projection. E and Z is more flexible than cis versus trans, and E versus Z is more preferred by the IUPAC. Cis versus trans can help you if you only have one substituent, but if you have more than one, E versus Z is better. Question: which of these is a mesocompound? Please pause. What is a mesocompound? Oh, it needs to have an internal plane of symmetry. Okay, let's try for each one. How about this? If I draw an internal plane of symmetry like this. So on the left side I have CH3, on the right CH3. On the left side OH, on the right. Oh, this is a mirror. So therefore, this is a mesocompound. Let's try this. If I imagine an internal plane of symmetry like this, CH3 and CH3. Yeah, but here's OH, here's H. This is not a mesocompound. Look at this one. Let's imagine an internal plane of symmetry like this. CH3 versus CH3. Look, H versus OH. This is not a mesocompound. Let me put an internal plane of symmetry here. OH and OH, amazing. H and H, okay, this is going to be meso, but be careful. CH3 versus CH2, CH3, this is not a mesocompound. Remember, when you are judging whether it's meso or not meso, you're talking about a singular compound within itself. I am not comparing this with this. I'm just talking about this. I am drawing a mirror inside a singular compound, not between two compounds. Would you consider this to be a mesocompound? The answer is yes, this is meso because it has an internal plane of symmetry. It has divided the same singular compound into two identical halves, left versus right. So what makes a mesocompound meso? It has a chiral center or centers as you see here and as you see there. This one has two chiral centers and has internal plane of symmetry. This is an internal plane of symmetry, and this is the internal plane of symmetry. The two halves of the same compound are mirror images of one another in the same compound. Let's talk about this compound. The two halves are mirror images in the same compound. I am not comparing this to anyone else. I'm just comparing the left half with the right half within the same singular compound. I can have an internal plane of symmetry between chiral centers as here, or through the chiral center. If something has an internal plane of symmetry, like these compounds right here, it means that they are not optically active. Racemic mixture versus mesocompound. Racemic mixture is comparing between two different molecules. Example, D-epinephrine versus L-epinephrine. These are two different compounds. But meso is comparing between the two halves within the same singular compound. One is inter, the other is intra. So here is enantiomers versus mesocompounds. Enantiomers, they have chiral centers. Meso, they also have chiral centers. However, because enantiomers do not have an internal plane of symmetry, they are chiral as a whole. And if something is chiral as a whole, the whole compound is chiral, therefore it has optical activity. But look at meso. Even though they have chiral centers, I have two chiral centers here, the molecule as a whole is achiral, non-chiral. Why not? Because I do have an internal plane of symmetry, which makes this achiral, which means optically inactive. The negative with the negative. If you are achiral, you'll have no optical activity. But look at these two enantiomers. No internal plane of symmetry. Therefore, they are optically active. This is chiral as a whole, and it's going to rotate to the left. This is chiral as a whole, and it will rotate to the right. This as a whole is achiral, despite having two chiral centers. As a whole, it's not gonna rotate light anywhere. It's optically inactive. By the way, this and this are identical. If you just rotate this a little, you'll end up here. Meaning these two are not different. They are the same freaking mesocompound. And there you have it, everything in one single slide. You can download these doozy notes on my website, medicosisperfectionalis.com. Here is the big chart for you. Here is enantiomers versus diasteriomers. And here is enantiomers versus mesocompound. And here is a lovely algorithm for you. How can I judge the molecule as a whole? Is it chiral and therefore optically active? Or is it achiral and therefore not optically active? Ask yourself the following questions. Do I have a chiral center? If the answer is no, we're done. This molecule as a whole is achiral. How about if we do have a chiral center? Ask yourself the next question. Do I have more than one chiral center? If the answer is no, I only have one chiral center, therefore the molecule as a whole is chiral. It is tilted, it is not balanced, and if it's tilted to the right or to the left, it's going to rotate the light to the right or to the left. But what if I have more than two chiral centers with an internal plane of symmetry? Oh, you are not tilted, you are balanced. You're not tilted, therefore achiral, and therefore you're not going to rotate the light anywhere. But what if you have more than one chiral center, no internal plane of symmetry, which means you're not balanced, no superimposable images, which means you're not balanced, you are tilted, you are chiral, and you will tilt the light either clockwise or counterclockwise. See, it makes perfect sense once you understand what the flip you're talking about. And here's a question for you. Which of the following compounds is optically active? You have choice A through choice H, and you can choose more than one. Let me know your answer in the comments. You'll find the answer key in the next video in this organic chemistry playlist. You can download my organic chemistry notes, my chemistry notes, my biochemistry notes, biology notes, physiology notes on my website medicosisperfectionalis.com. And if you like this playlist, you will enjoy my biochemistry playlist, my biology playlist, my general chemistry playlist, my physiology playlist, my hematology playlist, and much more. I have more than 1,500 free videos on this channel, plus more than 300 videos only for channel members who subscribe to the highest tier. Hit the like button, subscribe, hit the bell, support my channel on Patreon, PayPal, or Venmo. Go to my website if you'd like me to tutor you, or if you'd like to download my premium courses, notes, or cases. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine and chemistry make perfect sense.